Dear students, in this class, we are going to see the construction of the Smith chart. And the Smith chart is very much useful for calculating our transmission line parameters. Of course, already we know how to calculate the transmission line parameters like reflection coefficient, standing wave ratio, and the input impedance of a transmission line using our mathematical formulas. But in the olden days, all these computers and as well as your calculators are not available. At that time, our scientists have actually developed so many types of charts, tables and graphs, which will be useful to analyze so many parameters required for their analysis and design. And at that time, Professor Smith, in 1939, he developed an excellent chart which is known as a Smith chart. So, what is the use of using these Smith charts? Very simple. Without using your calculators and as well as computers, happily you can estimate all the transmission line parameters. Even a layman also can do this. But the only thing is it requires some practice. So, basically what is the Smith chart? How to construct it? I would like to explain in this class. So, Smith chart is nothing but a graphical representation of your reflection coefficient K in the complex plane. That means your reflection coefficient is having your real part as well as imaginary part. So, you know very well the reflection coefficient K is fundamentally defined as K is equal to ZR minus Z0 by ZR plus Z0. So, here what is ZR? ZR is nothing but the load impedance. You take a transmission line like this. This is nothing but your ZR. And the line impedance is nothing but your Z0, which is nothing but the characteristic impedance. So, as K is nothing but the ratio of impedances, impedance may be a complex. It is having both real part as well as imaginary part. That's why your K is also not a real number. It is an imaginary number having both real part as well as imaginary part. Kr plus some j times Ki. This is nothing but the reflection coefficient K. But remember friends, if you see this chart or otherwise this Smith diagram, and all the values will be inside this circle only. This is called unit circle. And if you take the radius of this is 1 and this is 1 and this is 1, this is 1. It is the unit circle. Inside the unit circle only you have to construct all these circles. So that's the reason, in order to accommodate the biggest values, biggest impedances, whatever the values it may be, if you want to accommodate inside, the only way is you have to go for the normalization. So what do you mean by normalization? Normalization means very simple. Suppose for example you take the load impedance ZR is equal to 50 plus J 100. This is a complex impedance. Okay. The characteristic impedance of the line is, let me say, this is equal to 100 ohms. So what is the normalization? Normalization means dividing each and everything by Z0. So I can say ZR by Z0 is equal to, okay, this is 50 by 100 plus J 100 by 100. This is called normalization, dividing by Z0. So just for the representation friends, I am telling you, ZR by Z0 I can say this will be equal to Z small r. So what is the meaning of Z small r? Z small r means normalized impedance. That is equal to how much? You can say this is equal to. So this is 0.5 plus J1. That means you can say resistance is 0.5, reactance is 1. So the definition I am telling you now, if you take the Smith chart is nothing but the combination of two types of circles. That is nothing but your resistance circle as well as the reactance circles. That's why if you take the Smith chart, it will be having two types of circles. One is R circles and other one is X circles. R circles means resistance circles, X circles means reactance circles. So, if you want to denote the impedance on this Smith chart, it is only the intersection of two types of circles. What are the circles? R circles and X circles. So I could like to tell you, these R circles and X circles are called as orthogonal circles. So Smith chart is nothing but very simple. It is nothing but the intersection of two types of orthogonal circles. One is R circle and X circle. And if you take this impedance, this 0.5 plus J1 means, what does it mean? It is an intersection of a resistance circle of radius 0.5 and the reactance circle of radius 1 ohms. So that's why Smith chart is basically consisting of two types of circles, R circles and X circles. And the second one is all the values will be within this unit circle only. And you see, this is the reflection coefficient having the real part Kr and as well as the imaginary part Ki. And if you take this K having a magnitude and as well as the phase angle also, because your K, reflection coefficient K will be equal to, it is having some magnitude as well as some phase angle. And here I am using for the convenience, the reflection coefficient is denoted by the letter K. But in most of the books, they are using gamma also, like this. This is gamma I and this will be gamma R, like this also. So just for simplicity, what I am telling is, I am using the letter K to denote the reflection coefficient. So reflection coefficient is not a real number, it is a complex number having real part as well as imaginary part. The real part is nothing but the circles, R circles, and your imaginary part is nothing but the X circles here. So it consists of two types of circles. Now I would like to explain you how to construct the R circles and how to construct the X circles, and then we would like to superimpose these R circles on the X circles to get the complete Smith chart. I think you understood this. Smith chart is having two types of circles, R circles and X circles. First, initially I can explain you how to construct R circles. Then I can explain you how to construct X circles. Then superimpose on those two. రెండిటి ఒకదాని మీద ఒకటి సూపరింపోజ్ చేస్తే you are going to get the complete Smith chart. And if you have a little practice on it, you can tell the answer of the problem within no time. Even calculators, computers లో చేసిన వాళ్ళకంటే కూడా ఫాస్ట్గా చెప్పొచ్చు. But only thing is, it requires some practice. So now let us see how to get this, how to construct this R circles. And you see, for getting this R circles, and once again I would like to take this reflection coefficient K definition in the normalized format. So just now I told you, you see K is equal to ZR minus Z0 by ZR plus Z0. Okay, ZR plus Z0. See, if you want the normalization, what would say? This is K is equal to normalization divided by Z0. ZR by Z0 minus 1 divided by ZR by Z0 plus 1. This is equal to Z small r minus 1 by Z small r plus 1. What does it mean? Z small r is indicating that the impedance is normalized. Normalized means dividing by characteristic impedance. Very simple. So your K is equal to ZR minus Z0 by ZR plus 1. So you can say this K is equal to, in the reverse I can say ZR is equal to 1 plus K divided by 1 minus K. So what is the value of this K? K is nothing but a reflection coefficient. It is not a real number. It is an imaginary number. So in the place of K, I can write down K is equal to Kr plus J times Ki. So I can substitute here. This is. So this real part is nothing but resistance circle, and this imaginary part is nothing but X circles. That's why for the denotation I can say K is equal to Kr plus J times Kx. X means reactance circles. So in the place of K, I can substitute here so that I can get some equation here. Okay. So now ZR is equal to 1 plus Kr plus J Kx divided by 1 minus Kr minus J Kx. So this impedance equation I would like to take as a basis equation for the construction of R circles as well as your reactance circles, X circles. Okay. For the constant resistance circles, just now I told you the normalized load ZR is equal to 1 plus k by 1 minus k, where k is a complex number, that's why I can write down 1 plus kr plus j kx divided by 1 minus kr minus j kx. So, if you do some mathematical arrangement and I would like to multiply the numerator and denominator with 1 minus kr plus j kx into, this is also multiplied by 1 minus kr plus j kx. And now just you multiply this, you are going to get Zr is equal to 1 minus kr plus jkx plus kr and minus kr, and this is plus kr minus kr square. So this is plus j into kr into kx, and this is plus jkx minus jkr into kx. This is j into j square is minus 1, that's why it is minus j minus k x square divided by 1 minus kr a minus b, this is a plus b, that's why I can say 1 minus kr whole square plus k x square, because a square minus b square, j square is minus 1, minus of minus is plus 1, this is. Now here kr and kr will be cancelled, and this is plus j kr kx into this cancelled, and this will be simplified as 1 minus kr square minus kx square plus jkx plus jkx 2j kx, j 2kx divided by 1 minus kr whole square plus kx square. Okay, right. So, if you just divide into real part and imaginary part, this Zr will be equal to the combination of resistance as well as reactance. What is the resistance here? Resistance. So, you can say that this is R plus J times X. This is nothing but the impedance. So, resistance is nothing but the real part. So, I can write here R is equal to 1 minus kr square minus kx square divided by 1 minus kr whole square plus kx square. So, this is representing the resistance circles, and as well as if you are just divided into real imaginary part, it will be nothing but the reactance circles. Therefore, I can say here x is equal to 2kx divided by 1 minus kr whole square plus kx square. So now we observed that there are two equations here, and this equation is telling about the resistance circles and this equation is telling about the reactance circles, because x is nothing but real. I am using a small letters here r and x to denote that they are normalized. Normalized means dividing by the characteristic impedance. Okay, right. So that's why for constructing these resistance circles, let me take this equation r is equal to this equation. R is equal to 1 minus kr square minus kx square divided by 1 minus kr whole square plus kx square. Okay, so cross multiply this is r into 1 plus kr square minus 2kr plus kx square is equal to 1 minus kr square minus kx square. Okay. So this is equal to, I can say r plus r kr square minus 2r into kr plus r into kx square is equal to 1 minus kr square minus kx square. So take this kr square into this side. This you can say that this is r plus 1 into kr square and this is r, and this is minus 2r into kr, and you can say that this kx square is equal to, this side if you take this, r plus 1 into kx square is equal to 1. Therefore, I can say, dividing each and everything by r plus 1, I can say that here this is equal to r by r plus 1. I am taking this r onto that side. This will be equal to 1 minus r. I am dividing each and everything by r plus 1. So, this is equal to kr square, kr square minus 2r by r plus 1 into kr plus kx square is equal to 1 minus r by r plus 1. This is. Therefore, this is equal to, if you write here, this can be equal to kr minus r by r plus 1 whole square into, so if you expand this, this is equal to kr square plus r by r plus 1 whole square, it is the extra term, minus 2ab. So, this is okay. So, the extra term is you are going to get here, this is equal to, you can say this is minus r by r plus 1 whole square is the extra term you are getting here, into plus kx square is equal to 1 minus r by r plus 1. Therefore, this is equal to kr minus r by r plus 1 whole square plus kx square is equal to 1 minus r by r plus 1, 1 minus r by r plus 1, and you take to this side plus r square divided by r plus 1 whole square, Then you take this LCM, this is r plus 1 whole square, and it will be r plus 1 into r 1 minus r, that means 1 minus r square, and this is plus r square. So, r square will be cancelled, this is 1 by r plus 1 whole square. So, kr minus r by r plus 1 whole square plus kx square is equal to 1 by r plus 1 whole square. So, friends, if you see this equation, it is nothing but a equation of the circle. So, what is the equation of the circle? I can say x minus h whole square plus y minus k whole square is equal to h square. This is nothing but the equation of the circle. And here, this is also the equation of the circle. So, I can say this particular equation is telling about the equation of the circle. So, what I have actually developed now, this is the equation of the circle. So, for this circle, what is the center? Center is hk and radius is a from your generalized equation. So, here the center of the circle is, center is r by r plus 1, comma 0. This is the center because kx is not having this. And the radius is equal to 1 by r plus 1. So, now what I would like to tell you is, for different values of r, I would like to construct these circles. Those circles are nothing but the constant r circles. So, this is the equation of a constant resistance circle having the center r by 1 plus r 0 and radius vachesi 1 by r plus 1. So, now substitute different values of r and calculate the center and radius. So, this table is actually telling about the center and radius for different values of r. So, put r is equal to 0, and if you take r is equal to 0, center 0, 0 and radius is equal to 1. So, radius is 1. And if you take 0.5, 1 by 2, so this is 0.5 by 1.5 means 1 by 3, 0, and this is 1 divided by 1.5 means 2 by 3 radius. So, if you take r is equal to 1, so 1 by 2 means 0.5 and 0, radius is also 1 by 1 plus 2, 0.5. So, like that the last value infinity. If you put r is equal to infinity here, so how to do this? R by r into 1 plus 1 by r, do like this, and 0 is the center. So substitute r is equal to infinity here. So what is 1 by infinity? It is 0. That means 1 and 0 is the center, and radius is 1 by infinity, that is equal to 0. So that is equal to 0. So you calculate the center and radius for different values of resistances. Now just try to plot this on the graph, and the graph is, I already told you, Smith chart is nothing but the implementation of the reflection coefficient in the complex plane. So if you take the complex plane, here it is the real part Kr, and this is nothing but the imaginary part Ki. That means Kx, that means x circles. Now you try to take the point here, that is 10.10, and just you take this point like this and plot all these points here. So if r is equal to 0, your center is 0, 0. So center is, this is the center, 0 and 0. And what the radius is? 1 here. So radius is 1. So this is radius is 1, and this is the radius is 1, radius is 1, and this is radius is 1. So you try to take a circle of 1 unit like this. This is the circle. This is the circle like this. So this is the circle of unit radius. This is the circle of unit radius, which is actually touching the point 10 here. And this is the for r is equal to 0. R is equal to 0 means the resistance is equal to 0. It is nothing but a short circuit. Okay, this is the biggest circle, and all other circles will lie inside this circle only. Okay, now if you take, this is 1 by 2. So what is 1 by 2? R is equal to 1 by 2, and its radius, its center is 1 by 3. 1 by 3 means actually it is 1 means it is 0.5. This is nothing but the 0.5. Okay, and 1 by 3 means 0.33, means it will be somewhere here. This is 0.33 like this. What is its radius? Radius is double than this. So 2 into 0.33 means 0.66. So definitely, and this will be the radius, and this will be the radius here. It will touch like this. So it will come definitely like this. This is the circle for the next one. This is the circle. And next one is 1. R is equal to 1 means 0.50. So this is the 0.5. This is the center of the circle, 0.5 and 0. This is 0.50. And the radius is this one radius. So you are going to get, this is the radius for this. This is the radius of this. So this is the third case. So similarly, you can go for these cases, and these cases radius goes on decreasing like this. That's why they may be becoming like this, like this. But remember here, all these circles are meeting the common point here, what is 1, 0. And if you take r is equal to infinity, r is equal to infinity means the center is 1, 0. This is the 1, 0 center. This is the 1, 0 point here. And its radius is 0. It is just like a dot. So here r is equal to infinity means open circuit. That means if you take a Smith chart, you are having constant r circles here, and this side is nothing but open circuit, and this side is nothing but your short circuit, because this is nothing but r is equal to 0. This is nothing but the constant r circles, and you can observe very clearly in this chart. And each and every circle is actually touching the point 1, 0. This 1, 0 point is nothing but open circuit, r is equal to infinity here. On the other side, you are having a short circuit. And these are the circles for different values of the resistances. And if you observe here, r is actually increasing from outer to inner. బయట సర్కిల్కి r is equal to 0 ఉంది. r పెరిగే కొద్దీ కూడా it is coming to the 1, 0 like this. This is called r is equal to infinity. So r is equal to 0 is the major circle. Inside all the circles are there. So r is equal to infinity is a point. From that you are going to get circles like this. But always remember, all circles will meet this common point, that is nothing but the 1, 0. So this is the way of constructing the r circles. Now exactly similarly, we are also going to develop x circles, which are nothing but the reactant circles. So after developing the reactant circles, if you superimpose these circles on this reactant circles, it becomes a Smith chart, because Smith chart is nothing but a Basically, it is nothing but a combination of two types of circles, R circles as well as XL circles. These are called as orthogonal circles. Orthogonal circles. Okay, let us see the construction of the X circles now.